Greetings and welcome back. Today we'll be looking at substitution reactions of ethers. The substitution reactions of ethers are largely very similar to the substitution reactions of alcohols, so I suggest that you review those briefly before moving into the rest of this video. So you may recall that ethers are carbons, oxygens, carbons. So they look generally like this. All right, those R's on either sides are carbons. They could be anything, methyl, ethyl, etc., etc. So ethers have very little reactivity. They're actually quite stable. The only case that you could make for any type of reactivity is that they do have lone pairs. So they can possibly be weak bases or very weak nucleophiles. But as they tend to be bulky, since they have R's on both sides, they're not very nucleophilic, and it turns out, again, they're pretty stable, so they're not very basic either. So ethers don't react with very much. The only thing that they will react with is very strong acids. So if we put these guys into a very strong acid, H+, what will happen is that the electrons of the weak base can bind to a hydrogen, which makes a new bond, and now we have some reactivity. We have an O+, and as you know, an O+ is a leaving group, and therefore the carbons next door are both electrophiles, and the hydrogen next door is now, of course, acidic. And essentially that gives us a gateway into the reactions of ethers. So reactions of ethers do not happen, if they're normal straight chain ethers, unless you first protonate them with a strong acid. All right, so what can we use to react ethers? Well, you have to have an acid, but the question becomes, what else do you put in with these? And if you put in with them some type of, I don't know, weak base or something like that afterwards, what will happen instead is that they'll just give that proton away, because you do have that acid, and they would just go backwards. So the only way that acids can react is if you put them in with an acid and something that is nucleophilic but not basic. And the only things that can do that are Br-, Cl-, and I-. So it turns out that really the only thing that acids react with, or excuse me, ethers react with, is HBr or Hi. All right, so if we protonate that guy, it becomes a positive charge, and then we would have a Br- floating around. Well, Br- is relatively stable, so it doesn't actually like to share its electrons. And the reactivity of Br- is that it's just a nucleophile, but not a base. Well, if we have a nucleophile and we have an electrophile, the reaction that we can have that will occur is that the nucleophile can attack the electrophile and kick off the leaving group. That would give us an alcohol plus a Br attached to R. And this is an SN2 reaction, and so this would be a substitution. So notice that what we've done overall is we cleave the bond on one side and replace, we basically substitute that oxygen group on the left. We substitute the oxygen for a halogen. So it's a substitution reaction. All right, but you still have some strong acid in there, and as we have seen, in fact, our reactions of alcohols showed us that if you have an alcohol and you have it in with HBr, the same thing can happen all over again. You can protonate that oxygen, which is that first step that we did above, which will give us a protonated alcohol. It has an O+. The reactivity of an O+ is once again a leaving group, and those hydrogens attached to it are acids, and the carbon attached to it is an electrophile. Well, now we have still a nucleophile floating around in the form of Br-. So essentially that exact same substitution reaction can happen again, where the nucleophile attacks the electrophile and kicks off the leaving group. We would then get an alkyl halide on the other side, and water. And we had an alkyl halide from the first side. And so what you can see here is that if you take an ether and put it into water, if we start off with the ether up here, if you put it into an acid, a strong acid in water, you will get cleavage on both sides of this. You'll do a substitution where you'll kick off the oxygen on one side and replace it with a halogen, and then you'll kick off the oxygen from the other side and replace it with a halogen. So what we end up getting overall is the conversion of that R group on the left side of the ether with a halogen, and the conversion of this R group on the right side of the ether with a halogen. The oxygen in the middle comes off as water because you protonate it twice. So that is really the only reaction that we can do to straight chain ethers. One thing to mention is that this only works, just like any SN2 reaction, with sp3 carbons. So SN2 only works with sp3 CXs. And therefore, if you have something with a double bond, it would be sp2. So this guy can do SN2. Something like this cannot. All right, so I'll give you a couple examples of this, and I'd like you to come up with the answers for them. All right, so let's move into some very specific ethers, which includes a new functional group we haven't seen before. So this is a three-membered ring that has 2 carbons and 1 oxygen. And this guy is a new functional group called an epoxide, or an epoxy ring. Essentially, it's just an ether, but it's specifically in a 3-carbon ring, and so there's something very unstable about it. What is that that's so unstable? All right, so yes, the interior bond angles are way too small. This guy would like to be 109.5 degrees, but instead they're about 60 degrees because it's a triangle. So there is a tremendous amount of ring strain. This guy really just, that ring wants to open up so everything can have 109.5 degree angles, and so it is quite unstable. You may have heard about epoxy resins before. Epoxides are often used for glue because they are very reactive, and you can make long chains of them in polymers readily. But that's something we'll get to a little bit later. For right now, we want to look at their reactivities. And the reactivity of an epoxy is actually very similar to the reactivity of any ether. So the way that we just did reactions of ethers is that we can add first some acid, which protonates the oxygen and makes it a very good leaving group. And in this case, we can combine that with usually a weak nucleophile. The other way to do this is for an epoxide, because they're so unstable, you can also, if you choose, react them with a strong nucleophile. All right, so before we get into the specifics of that, let's have a specific example of an epoxy. So we'll do this guy right here. I'm just going to give it one group coming out here. We'll give it a CH2CH3. Then there would be an H back there in the back, and we'll just say that there's 2 H's on the left side over here. All right, so we have 2 ways that we can react these epoxides. One is to add a strong nucleophile, and the other is to add a weak nucleophile. So let's do the weak nucleophile first. If we take this guy and add in an acid, what would occur is that the electrons on that oxygen would grab onto the acid. This is the same thing as that first step in the reaction of alcohols that we talked about already, and also ethers that we talked about in just the slide before this one. So at that point, the hydrogen would be protonated, the oxygen would have a plus charge, it would be a very good leaving group, and therefore the hydrogen would be acidic, but very important to this is that both of those guys would be electrophiles. And then we can add in a weak nucleophile, and a lot of times we would just do this at the same time. So let's say that we put a little bit of acid in methanol. Well, the acid would react first, because the methanol is not a very strong nucleophile. But this guy is a weak nucleophile, and so I'd like you to see if you can tell me what you think will happen. All right, so this ends up being an SN1 reaction And in SN1 reactions, effectively what happens is the leaving group leaves first. Well, the leaving group doesn't really leave first, but it really tries to leave. And as you know, leaving groups tend to leave in SN1 reactions when you have a very substituted CX. The reason for that is it would form the most stable carbocation. So the leaving group wants to leave the side with more carbons attached, and therefore that carbon would be the strongest electrophile, and therefore your nucleophile would attack the electrophile over there. This would result in breaking that carbon-oxygen bond on the right. So we would have that OH would still be attached on the left, and we would still have the H's there. That second carbon, which is the one that was the electrophile, would have a new bond to what was the nucleophile. And we would still have that CH2CH3 over there. So this might look a little bit weird, but let's take this one step at a time. So the leaving group, which is this oxygen, wants to leave, and the easiest carbon for it to leave is the most substituted carbon. The reason for that is that the more substituted carbon gives you the more stable carbocation, and therefore when you have a very good leaving group in a three-membered ring, it wants to leave the carbon with the most carbons attached, so it leaves the most substituted side. Therefore, the weak nucleophile would attack the carbon on the most substituted side, and we would have a new bond down here between the carbon that was the electrophile, so this is the one that was in that three-membered ring, but is now just sitting over here by itself. It has a new bond to the oxygen, which was the weak nucleophile in that methanol. Of course, you remember at the end of SN1 reactions, we often have to do deprotonation, and so we will do deprotonation again. I will draw it out for you. It's just an acid-base reaction. The O plus is a good leaving group, and therefore it's very easy to pull a hydrogen off of it. And this would result in the formation of a new molecule in which we broke that epoxy by attacking it on the most substituted side. There would be a methanol that is now protonated, so essentially you'd have just a low pH or a lower pH methanol solution. But this is your final product. All right, so let's look at what would happen if you add in a strong nucleophile instead. So I'm going to add in not an acid, but just a strong nucleophile. I'm going to add CH3O-. So a methoxide. And I will add methanol, but only as the solvent. So methanol is a weak nucleophile. Methanol is a weak nucleophile and also a weak base. But that methoxide up there, that O-, is a strong nucleophile and a strong base. All right, so what do strong nucleophiles do? Right, so strong nucleophiles do SN2 reactions. You will remember that SN2 reactions always want to attack the least substituted CX. Because it's easier for the nucleophile to fit in there. So if we look at the two possible electrophiles, well, the leaving group isn't a really great leaving group, so neither of these electrophiles is particularly strong. So in the example to the right, the reaction we have over here, if we protonate that oxygen, it makes it a really good leaving group, and so both of these guys are very strong electrophiles. The strongest one is the most substituted one. So if we have a weak nucleophile, we can attack the most substituted side. If you add a strong nucleophile in, well, that guy can just drive itself in there and kick the oxygen off. Not because oxygen's by itself a very good leaving group, but because this is a ring-strained and especially unstable ether, and therefore we're able to attack it with a strong nucleophile or a strong base. We don't have any acids, so this guy can't act like a strong base, but we do have electrophiles. And in an SN2 reaction, you attack the most readily accessible or the least substituted side. And that would give you a new molecule where that bond on the left side is broken. We've attached an OCH3 over there. and we would still have our CH2, CH3 attached on the right. Well, now that you've kicked electrons up to that oxygen, it makes an O-, and so that's where the methanol comes in. You do this in a solvent. So if you think about it, way over here we had an extra hydrogen, so we just used the solvent to pull it off in a step we call deprotonation. Well, here we have an O-, and so it doesn't quite have enough hydrogens, and so this guy can be protonated. It can just simply pull a hydrogen off of a weak base sitting around. So this guy can grab one of those hydrogens, the electrons there would kick over to that O, and we would protonate that guy. So notice the difference in these two approaches. If you start with an epoxide, we can, depending on which nucleophile we add, we can choose to attack the most substituted side of the epoxide by adding an acid followed by a weak nucleophile. We can choose to attack the least substituted carbon in the epoxy by adding a strong nucleophile with a little bit of base. And so those are the two ways that we can choose. And big picture, we add whatever we want, and it depends on which product we want to do, or we want to form. If we want to form a product where your nucleophile attacks on the least substituted side, then we should add a strong nucleophile. If we want to make a product where our new group is found on the most substituted side, then we add a weak nucleophile and some acid. All right, so let's practice one of these, and then if you have any questions, please bring them to class. Thank you very much. Have a great day.